let's have a look at some HSC. Here's one of the more recent ones, last year's 2014 paper. And so we had our standard hyperbola, x squared on a squared, y squared, b squared equals 1. Basically, they're setting the question up. S is the focus, AE naught. They've defined 2 points. They're not on the hyperbola, they're on the asymptotes. So they've called them AT, BT, because that one is on the line y equals b on a x. And the other one is a on t minus b on t, because it's on the line y equals minus b on a x. Where t is greater than 0. And what have they then told us? The point M is the midpoint of PQ. Now on the diagram it says it's on the hyperbola, but if I remember correctly, yes, the first part of the question was to actually show it lies on the hyperbola. Bit of a gift mark to start off with, really, because all we have to do is substitute it into the equation of the hyperbola and show it satisfies the hyperbola. So x squared on a squared minus y squared on b squared, subbing in those x and y coordinates. Then we've got a squared that'll cancel with the a squared, b squared with the b squared there. We then have a common denominator of 4t squared. So on the top we've got t plus 1 all squared minus, t squared plus 1 all squared minus t squared minus 1 all squared. So we have a perfect square minus a perfect square. So we should be left with 4ab, or 4 times the product. But because this was a show that question, I didn't want to go straight to 4t squared, because it might look like, oh, I've just jumped to there, and so that equals 1. So I actually did bother to expand the whole thing out so we could see, oh, well, yeah, that is 4t squared on 4t squared, which is 1. So yes, M does lie on the hyperbola. Okay. Prove that the line through P and Q is a tangent to the hyperbola. Slope of PQ ends up being b on t squared plus 1, a on t squared minus 1. Now, I found the derivative of our hyperbola there, b squared x on a squared y. I've found that the slope at M is also b t squared plus 1, a t squared minus 1. So it does equal the slope of PQ. So well, I know PQ is parallel to the tangent, but as it goes through M, then it's not only parallel, it must be the same line. Now the fun part. Show that OP times OQ is equal to OS squared. So OP times OQ. So I've just gone straight to the distance formula. Multiply them together. I've taken out a common factor of t squared in the first one, 1 on t squared in the second one. So t times 1 on t, that'll cancel. Leaves me with the square root of a squared plus b squared times the square root of a squared plus b squared, which is a squared plus b squared. But remembering with a hyperbola, a squared plus b squared is the same as a squared e squared, right? Because it all comes from e squared being a squared plus b squared on a squared. And so that is ae all squared, and obviously the distance from the centre to the focus is ae. I thought I probably should explain why I could just jump straight to a squared, e squared there, because remember, again, it's a show that. So that's why I bothered to put that definition down on the right-hand side there, so it doesn't look like I've just fudged it. Now, if P and S have the same x-coordinate, now we're going to show MS is parallel to one of the asymptotes. Okay. If P and S have the same coordinate, then I now know that AT is equal to AE. Because the x-coordinate of S obviously is AE. But we said P had an x-coordinate of AT. So therefore what we're basically saying is T, the parameter in this case, is E. Well, the slope of MS then, if I find that slope after we play around with it a bit, minus B on A. Well, minus B on A is in fact the slope of one of the asymptotes. So this question really was just a lot of algebraic manipulation, to be honest. Although we did have to use, there it is, that definition, E squared, back in part 3. That was the first question last year. The second conic question was this. The point, and they gave it to us in parametric form of the ellipse, again the standard ellipse. The acute angle between OP and the normal to the ellipse of P is phi. Show that tan phi is that expression there. So in other words, the angle between these two lines. All right, we want to find the acute angle between two lines. We have our absolute value of slope 1 minus slope 2 over 1 plus slope 1 times slope 2. So I need to find those two slopes. So to find the slope of the normal, well, let's differentiate a cos theta, and then I'll differentiate b sine theta. Putting it together, dy dx is our standard minus b cos theta on a sine theta. So therefore the slope of the normal will be the negative inverse of that. So we get a sine theta on b cos theta. The other slope I want is the slope of OP, and so that would just be b sine theta over a cos theta. Subbing into our acute angle formula, we actually do have a common denominator there of AB cos squared in both the top and the bottom of the fraction, although I will have to multiply the 1 by that as well. Now, on the bottom of the fraction, what have I done? Oh, I've left the A and B on the bottom there for some reason. I wonder why I did that. But anyway, we end up with cos squared plus sine squared on the bottom, which is, of course, 1. So, now I have, if I make it all one fraction, there's the AB. A squared sine theta cos theta minus B squared sine theta cos theta. Very close to what they want. A squared minus B on AB. Absolute value of sine theta cos theta. Now, and this is where I had a problem with last year's exam, because if you look at what they asked you to prove, I don't think it's true. It's only true if theta is acute. Now, who's to say that theta, because remember what theta measured is as P goes around, or at some point theta is going to be obtuse. And then that relationship's not true. So that's why I put absolute value in there and then made a statement, well, okay, if P is in the position that's in the diagram, theta would be acute, so then I can say, all right, it's times sine theta cos theta, which is what they wanted to show. I actually disagree with what they want to show. Find the value of theta for which phi is a maximum. Right, well, sine theta cos theta, I can think of that as a half sine 2 theta. I don't need to worry about calculus. A lot of people would, I guess, waste time, differentiate to maximise it. But it's a trig function. And we know things about trig functions. We know it's a maximum at 90 degrees, or pi on 2 radians. So that'll be a maximum when 2 theta is pi on 2, because the sine curve will be at its amplitude. So if 2 theta is pi on 2, then theta is pi on 4. As a squared minus b squared on ab is a constant, that's not going to change. Then it's fair enough to say tan phi is a maximum, because it's only that trig part that's changing. So really I just have to find when the trig part is a maximum. The question is not actually asking when is tan phi a maximum, it's asking when is phi a maximum. So I've found when tan phi is a maximum, that's when I talk about the increasing function. Right. So if tan is an increasing function between 0, pi and 2, then the maximum value must happen at the maximum angle, because it's continually increasing. The 2013 paper was 12D. It was a rectangular hyperbola. We're told P and Q are 2 points. They're on different branches of the hyperbola, but we also know that the parameter P and Q are not like symmetrically opposite. So the absolute value of P doesn't equal the absolute value of Q. The tangent to the hyperbola intersects at A and B, and the y-axis, oh yeah, done that. Similarly, the tangent at Q intersects C and D. Okay, so they've set up the question for us. What's the first part? There you go. A straightforward, let's pick up some gift marks, find the equation of a tangent. So, all right, I'll differentiate. At x equals cp, slope is minus 1 on p squared. Point slope formula, bang, that comes out. Show that A, B, and O are on a circle with centre P. Okay. If you have a look in that diagram, triangle AOB is right angled and AB is the hypotenuse. So I could waste a lot of time here, but if I look at the picture and use some geometry, it's very quick. So AOB are concyclic, with AB being the diameter. Anytime you've got a right angled triangle, you know there's a circle that must go through all 3 points of the triangle. And the hypotenuse must be the diameter, because the angle in a semicircle is 90 degrees. Okay? So that's all I'm using, just that basic idea of angle in a semicircle is 90 degrees. Now, the centre of the circle, what's going to be the midpoint of AB? All right, let's find the coordinates. At A, y is equal to 0, so x is 2cp. At B, y would be 2c on p. There it is. The centre is P. And that's what we wanted, with centre P. Okay, so yes, found all the things they want. AO and B lies in a circle. The centre is in fact P. Prove that BC is parallel to PQ. Lots of interesting ways of doing this question. The way I chose to do it was like this. I drew in the 3 lines, BC, PQ, and AD. Okay. Now, we just said P is the centre of a circle that passes through A, B, and O. Well, similarly, because if you look at the other branch, that other tangent is set up exactly the same way. So it must also be true that Q is the centre of a circle passing through D, C, and O. In other words, AB is the diameter of a circle, so AP equals BP. But CD would also be the diameter of a circle, so CQ equals QD. Equal radii. So the ratio of AP to BP is the same as the ratio of DQ to CQ, which equals 1. Well, that's our property of transversals on parallel lines. Those transversals cut in the same ratio. So therefore BC is parallel to PQ, is parallel to AD via our ratio of intercepts of parallel